In this video, we'll be discussing the chi-squared analysis, which is one of the inferential approaches that we'll specifically discuss within this class. Now, when thinking about the chi-squared, it can be helpful to understand it within the context of our classic inferential options. So classically, we look at two variables, the independent and dependent variables. And we look at the classification of the variables as we discussed in the first lecture set of this course. We look specifically at whether or not the independent variables are continuous. So we'll have, independent and dependent variables are continuous versus categorical. So we'll have continuous and categorical listed for the independent and dependent variable. And depending on the mixture of those, we have different analytic options. This table is a pretty good summary, I think, of those analytic options. We have the independent variable, categorical continuous, and the dependent variable, categorical continuous, and then the four analytic options depending on which mixture we have. So when the independent variable is categorical, we have two options. We have when the dependent variable is also categorical, which would be a chi-squared. Think about looking at the differences between male and female on which political party you vote for. Both of those are categorical variables. Independent variable is male-female. Dependent variable is political party. When we have an independent categorical variable, we can think of the male-female again, and a dependent variable is continuous. Think of how excited you are about taking part in political voting on a scale of 1 to 10. That might be a continuous scale. That would be categorical and continuous, which would indicate an ANOVA analysis. ANOVA stands for analysis of variance. If the independent variable is continuous and the dependent variable is categorical, so let's say we're looking at the impact of age on the political party you're affiliated with, this is called a logistic regression. And if the independent variable is continuous and the dependent variable is also continuous, so where we're looking at the impact of age on how excited you are to vote, then this analysis technique is called a regression. Now, I want to note that while these are some bread and butter statistical methods, these are certainly not a complete list of statistical methods or even a complete list of the important statistical methods. This is, I think, a reasonably sound baseline to begin with. It gives you some basic options within each of the worlds. And there's a variety of extensions within each of these that can go further than what we discuss here. So take this as kind of a primer list of a couple of handy things. It's like if you're learning a new language, this is teaching you hello and can you help me? And I don't speak this language very good. This is teaching you a couple of basic things that can help you get by in a wide variety of situations. But again, it's certainly not comprehensive. Now, I will say for one of these, the one in the top right, logistic regression, this has some very complex interpretations, and we'll briefly touch on some of that in this lecture set for the chi-squared. So what we're going to say for the purposes of this class is if you ever run into one of the cases with logistic regression, and for whatever reason are limited to the tools you've learned in this course, what I'd recommend is that you simply split the continuous independent variable into categories, maybe low, medium, and high, or just low and high. And if you split the continuous variable into categories, now you have an analysis technique that can handle a categorical independent variable with a categorical dependent variable. So that would essentially turn, again, this continuous variable into categorical and essentially turn our logistic regression into a chi-squared analysis. So if you're limited to the tools we'll talk about in this course, That is a technique that you can use. What's interesting about this is that you could actually do this approach to move all of these analyses to be chi-squared. You could always move from continuous to categorical. You just categorize. I think we mentioned our continuous variable is age. I could have age below 40 and age above 40. Well, now I've got two categories, category 1 and category 2. And you can do that with your continuous variable. You can do that with your dependent variable. We talked about how much you are excited about going to vote. So scale of 1 to 10. We could have below 5 and above 5. I'm not really excited. I'm excited. So I can always move from a continuous variable to a categorical variable. I'll note this doesn't work backwards, so I can't move from a categorical variable to a continuous variable. That is, if you say I'm below 40, then that doesn't tell you how old I am. Again, if I know how the age is, I can always go to that correct category. But if I know the correct category, I can't then go to the age. So we do lose information when we walk backwards here. But we can always walk backward, which essentially, if we ran into problems with any of these and we wanted to simplify the problem a bit, we could turn all of these into chi-squared analyses. Because of this, chi-squared is one of the most fundamental analyses we have. As one of my former professors, recently deceased Jay Schaefer, put it, if I were stuck on a desert island somewhere and I only had one statistical analysis I could bring with me, this would be the one. And it's because it's applicable to so many different circumstances if you need to use it in a pinch. And that's a big pro of this method. A second pro, incidentally, is that this really doesn't have many or really any statistical assumptions. And we'll discuss some of these briefly with other tests, but long story short, there's a few assumptions that we have to make all of the other analyses work. And if those are ever violated, that can cause errors to happen more often than we believe. So for instance, I could have a think that my alpha level is representing a 0.05, a 5% error rate, but the actual error rate, because of the violation of the assumptions I've made, is even higher. It could be a 10% error rate, and I wouldn't know it. I'd be making errors more often than I'm comfortable with. And so that's the violation of statistical assumptions. Again, the pro here is chi-squared. It doesn't have many or really any. We'll talk about one. But I wouldn't even call it a statistical assumption. So it doesn't really have any of these assumptions, which is fantastic. Now, there is a con when it comes to simplifying information. And that is that this uses the least amount of information of anything on this screen. So it has the least statistical power of any test we'll discuss. Now, that doesn't really matter if I'm dealing with independent variable categorical, dependent variable categorical, because there's no other analytical method that can even begin to address that question. But if I'm talking about simplifying continuous variables down to categorical variables, as we've alluded to earlier, we actually lose a lot of information. And what that turns into from a statistical perspective is losing a lot of what's called statistical power, or the probability that we find a difference if it's actually there. Our tests become less precise, they become less specific. And because of that, it's always considered best practice to utilize the information that you have when you can. So when you do have continuous variables, we tend to not recommend simplifying them down if at all possible. In this class, we're simplifying down the logistic regression situation to a chi-squared if it ever comes about. And the reason we're doing that is just because of the complexity of interpretation of the logistic regression and the fact that that goes through that beyond the scope of this class. So this is what we're going to be talking about today, this chi-squared. It's up to 2 of the 4 cases you could run into. And what you'll like, hopefully, is that it's the computational easiest of the 4. So this is the analysis we're going to be working through. It's a pretty cool one. I like it a lot. Again, really, really flexible. So this is our lecture set for this week. All right, so our chi-squared, as we've discussed, is used to assess categorical variables. Now, previously I mentioned an independent and dependent variable. We'll discuss through this lecture set that the chi-squared can be used to assess a single categorical variable, or we can compare relationship between multiple categorical variables. We can do even more than two categorical variables if we want to, which we won't discuss in class, but is possible. So there's any number of categorical variables. If you're looking to assess that, a chi-squared can be a handy analysis to utilize. Now, ultimately, what we're going to be doing in the chi-squared is not actually analyzing the categories itself. And so I want you to think about maybe the location of a patient. If they're in the urgent care, if they're in the emergency department, the ED, or if the patient is maybe in a long-term care ward. So like different classifications, I guess is my goal, different types of patients. And what we're going to do is we're not going to analyze the category names or anything like that specifically. I remember when I first learned about categorical data, I was like, so are we gonna like, I mean, they're just descriptions of things. Are we going to like analyze the letters or something? No. That's not how we're going to approach this. What we're going to do is we're going to count how many people are in each category, and then we're going to test some assumptions about the counts. So let's say I assume that I have an equal proportion of patients who are admitted, an equal proportion of patients in the ED, and an equal proportion of patients who are in the urgent care. And so I'm going to count how many patients are in each of those categories and see, do those counts align with that assumption, and test that. So that's what we're doing, is we're still analyzing numbers, but now we're analyzing counts within categories. And that's how we approach the data analysis within the chi-squared, the categorical context. Now, when we create these counts from the categories, those are formed into what's called a contingency table. And we're actually going to take a little bit of time to discuss that coming up here in a slide or two. And pretty much all that is we write out each of the possible categories you could fall into and count how many people fell into that category. And that's a contingency table. Again, the chi-squared analysis is comparing those observed values that fell into that bin to what we would have expected under a null hypothesis. In the case I described, I assumed that all of the groups have equal numbers of patients. But maybe there's a reason to believe, hey, in the region, this one is this percentage of patient load, this one is this percentage of patient load. And we want to determine, do we align with that, or are we different than that? And if we are different than that, how are we different than that? This could be useful for things like staffing decisions. Hey, it's tended to recommend put X amount of staff here, X amount of staff here, X amount of staff here. Well, that works if our patient loads are equivalent to everybody else, and we can test that. Are the counts that we're seeing the same as the percentage that the rest of the industry describes? And if that's not the case, then maybe we shouldn't also follow general staffing decisions. Maybe we need to tweak those to address the differential patient load. Now, when we're working with a single categorical variable, and I'm talking about patient load in a couple of different categorical contexts, often what we compare to in our analysis is a pre-hypothesized count or a pre-hypothesized percentage. So in this case, I'm saying all of them are the same, or hey, maybe there's a regional standard as to the percentages of patient load from each of these different wings of our hospital, our hypothetical hospital with three kind of weird wings. But that's how we would get these pre-hypothesized, null hypothesized counts, is from this. And we could either use counts or we could do percentages and then make the counts based on those percentages. That's something that'll be very easily accessible for us. Now, if we have multiple categorical variables, this changes a little bit. Let's say I have hospital A and hospital B, and I want to test if their patient makeup is the same. So here I would have one categorical variable, that's the outcome, that's the category of patient, and I'd have a second categorical variable, that is the independent variable, that is the hospital, and I want to test, do the hospitals differ on that categorical outcome? Well, the mathematical way of saying that is that the hospitals are independent of the categorical outcome. That is, it doesn't matter which hospital you're at, the categorical outcome is going to be the same. Or it doesn't matter which category you are, the probability of being in either hospital is the same. So we're going to build the null hypothesis on the assumption that the variables are independent, and then test, is there actually a relationship? Do they depend on one another? That is, does the patient makeup depend on what hospital you're at? If so, then we would say the hospitals have a different relationship. And if the patient makeup doesn't depend on what hospital you're at, then we would say that the hospitals don't have a relationship with the patient makeup. As we'll discuss when we get to there in this lecture set, the first case is called a chi-squared goodness of fit. And ultimately, it checks how well the pre-hypothesized counts, percentages, distribution fits with the data. So goodness of fit. How well does our data fit with those counts, percentages? The second one is called the chi-squared test of independence. And this is to see if the variables are independent from one another. So you'll sometimes see these chi-squared tests labeled different things. And for me, when I first learned about it, it was confusing because, as we'll find out later, the equations are exactly the same. The different tests regard the different situations. Are you comparing your data to a pre-hypothesized count or percentage? If so, you're comparing the fit of your pre-hypothesized percentage distribution to the data. So you're checking the fit, called goodness of fit. Versus, are you testing if variables are independent from one another? And if so, we call that a test of independence. So ultimately, we're just being a little bit more specific about exactly what we're testing with this chi-squared. As we'll find out later, again, this is actually the same equation for both of these. We're just looking at them in a slightly different context. In the first case, often done if there's a single variable, and the second case requires multiple variables. Now, all of these happen in the form of the contingency table. So a contingency table, there's a lot of names for this. Sometimes you'll see it called a frequency table, a confusion matrix. In SPSS, it's called crosstabs. There's even more names for this that I can't think of off the top of my head or when I was making this slide for this slide deck. But lots of names for this contingency table. And all it is again, a table of what are all of the options for the categorical variable, maybe we have more, and then how many individuals fall within each of those options. Now, for two variables, how we track this is we make a little a table. We make a little matrix. We have across the rows, in each row as a header, we have all of the options from variable A, and in each column as a header, we have all of the options from variable B. And then wherever the option from variable A meets the option from variable B, we write how many people have both of those. So how many people are in both of those categories at the same time? And again, because there are two different variables, we expect people to have a mix of categories. For instance, we could look at how many males are voting Democrat, how many males are voting Republican, how many males are voting independent, how many females are voting Democrat, how many females are voting Republican, how many females are voting independent. So you can kind of see or feel that each of those are actually two different variables, the political party and the male-female variable. And within each of those combinations, we'd have a different count. So when we make the contingency table with two variables, or if we do it for even more, though with more than two, it's hard to visualize. If we do this with two variables, we do it for each combination of the levels. And remember the levels, when I say levels of a variable, that just means what are the possible response options. So if I ask you to list your sex, the levels are going to be male, female. in one particular study. If I ask you to list your political affiliation, the levels might be Democrat, Republican, Independent in one particular study. So when I say levels, it's just what are the options, the response options that you provided to participants. So I feel like when we talk about this, it's harder to explain than to just look at. So let's just look at one. So we have a table. I'm gonna put in some stuff. So I'll add the levels of the variable. In the columns, I'm going to have the type of antibiotic that was prescribed. And then the rows, I'm going to add whether or not the staff went through our antibiotic training protocol. So if they did go through the training protocol, then they would be in the top row, and if not, they are in the bottom row. And now we're going to look and see which of them are assigning broad spectrum versus narrow spectrum antibiotics in their most recent case. So here we're just looking at the counts, and again, if I'm looking at any particular cell here, I would see for this particular cell, I'd write a number. Let's say I wrote the number 57 or 13 or 38 or whatever. 57 represents that there were 57 individuals who went through the protocol and assigned narrow spectrum antibiotics. There were 13 individuals who went through the protocol and in their most recent prescription assigned broad spectrum antibiotics. There were 38 individuals who didn't go through the protocol and assigned narrow spectrum antibiotics in their most recent antibiotic prescription, and there were 30 who did not go to the protocol and assigned broad spectrum antibiotics in their most recent antibiotic prescription. So this is how we break this information down, and this is what that represents. Again, each cell represents a number of people who did both things, both the thing in the column and the label in the row. So again, that 57 represents somebody who went through the protocol and assigned narrow spectrum antibiotics. Those are the number of people. 57 people did both of those. All right, so let's toss that off to the side here and note a couple of notes on notation. So we're going to use the subscript I to represent the rows and the subscript J to represent the columns. Now this changes depending on the context and who you talk to. Some people do R and C instead of I and J. Some people do different things here. So it just depends. But we'll use I to represent rows and J to represent columns. And it's good to keep in mind, it's not going to be hugely important within this class, so don't stress too much about it. All right, so for the observation of row 2, that is, they did not go through the protocol. Column 1, that is, they gave a narrow spectrum antibiotic. We'll use O sub 2, 1 to represent the observation in row 2 and column 1. So you'll see I, comma, J as a general representation, and the O notation used to represent an observation. In this case, O sub 2, comma 1 is 38. There were 38 people in row 2, column 1, or 38 people who did not go through the protocol who assigned narrow spectrum antibiotics in their most recent antibiotic prescription. All right, so let's quickly, and I apologize, this is a bit of an aside in this class, but I feel like we should really talk about it because it is something that comes up, especially in medicine, is this confusion matrix. Now, a confusion matrix is a specific type of contingency table, and we do this to show prediction accuracy. Which might sound a little bit weird, but think about in medicine, we're trying to predict whether there's a disease or not. You could be looking at this from like a test perspective. You could be looking at this from a diagnosis perspective. You could be looking at this from a procedural perspective. So there's a lot of different ways to do it, but ultimately you're trying to guess, is there a disease or not? And you're either right or you're wrong. And frankly, you're never going to know if you're right or you're wrong, potentially. You may never know if you're right or you're wrong. But you still have to guess. And so we make a guess, and there's as with our inferential statistics, when we make a guess as to what's going on in the population, there's a mix of conditions that can happen, ultimately boiling down to we got it correct or we got it incorrect. So again, this isn't a main focus for this lecture or this lecture set, but let's do this because, or let's spend a bit of time going through this because this will bring up some important things that will come in to play later in our lecture set. And we'll also discuss a few kind of notational things and a few definitional things, some calculations that you may see later in your program, or you may be currently seeing in your medical practice. All right, so we're going to start with a table similar to before. You'll note that the columns represent the reality of the situation. Either the patient has the disease or the patient does not have the disease. The rows represent our predictions or diagnosis. We have diagnosed the patient with a disease, or we have diagnosed the patient with no disease. Again, all this information, specifically the columns, isn't always available in medical contexts. So we don't always know if the person has the disease or not. We're just trying to make our best guess. Now, again, each entry in this table represents either an accurate diagnosis or an inaccurate diagnosis, which we'll denote in this way. Here, TP in the top left is going to represent the true positive. FP in the top right is going to represent a false positive. So that is, we predicted you had the disease, but you actually didn't. So the positive represents the prediction, or goes back to kind of testing notation in terms of a medical test. The tests tested positive, you had the disease, but actually it was false because while it tested positive, you actually don't have the disease. Anyway, moving on, in the bottom left, we have FN representing false negative, and the bottom right representing TN representing true negative. So you'll see that true are in the top left and the bottom right. It's called the diagonal of the matrix. And the falses are in the bottom left and top right, called the off diagonal of the matrix. So here, again, we have two ways we could be true, either correctly predicting the disease or correctly predicting the lack of disease, and two ways we could be false, incorrectly predicting there's a disease when actually there wasn't one, and incorrectly predicting there was not a disease when in fact there was one. Now, this notation is only for confusion matrices and not for general contingency tables. And I'm just introducing this quickly so I can go through a couple of the statistics that come from the contingency tables. But in both confusion matrices and in regular contingency tables, we often add information to the base table. So we've got this base table, but often we add information kind of out on the, what we call in the margins of the base table. So I'll show that here in our margins. Now, this information that we often use is the total column. So in the total column, I would add up, let's say I'm looking at this particular total cell, and I'm looking to figure out what to enter into there. This would represent everybody within the column. So this is all of the people that have a disease. That would be my patients that I predicted correctly. I told them they had the disease, and they actually did. This is also patients that I told them they didn't have the disease, but it's a false negative. I was incorrect with my prediction or diagnosis. So here, all of these individuals have the disease, and they would be summed up in this total. Often we use sums. Sometimes you'll use an average, but often we use sums in the margins of a contingency table and a confusion matrix. And again, these marginal values are often calculated in both the confusion matrix and the more general contingency tables. Now for the rows, if I'm entering this cell, I'll add up all of the components from this row. So here, This particular cell is going to be the total number of people where I predicted they have the disease. So this is going to be my true predictions and my false predictions. The people I predicted both of these got the disease. This is all the people I predicted who had the disease that actually had it, plus all the people I predicted had the disease who didn't actually have it. And altogether, those make the total number of people I predicted had the disease. The notation for our marginal cases for just the confusion matrix, we'll use P to represent the total number of true positives, N to represent the total number of true negatives, PP to represent the total number of predicted positives, and PN to represent the total number of predicted negatives. Now, again, this notation is not typical in a regular contingency table, but is more typical in a confusion matrix. One thing is that the sample size, which we typically write as N, I didn't write as N here because I didn't want to get it confused with the N, the total number of individuals who do not have the disease. So I'm using SS to represent sample size. When we get to our main contingency, when we get to our main, contingency table, we will change that notation slightly. So just a heads up on that. Now, what's really cool about this is kind of the total table, is that there is an immense amount of information packed into here. More than you would think, a lot more than you would think, a lot more than many people think. So let's look at what we can pull out using just information from this table, those 4 values. Now, I'll be 100% honest. The information is stuff that I don't use often enough to remember all of the formulas off the top of my head, nor do I use this often enough to remember the specific interpretations off the top of my head. Well, for some of these I do, I guess, but for the trickier ones, I sure don't. Plus, there's a bunch of others that we're not going to discuss. So what I'm going to recommend and try to help you with is to focus on the system by which we can look at the ratios, and we can apply it as needed. So let's start with one, and then we'll work through what I mean. So the true positive rate, which we also sometimes call the test sensitivity or recall or hit rate, is the number of true positives over P. And if you remember from our previous explanation, P, and maybe you need to jot these things down so you do remember, is the total number of patients who had the disease. So of the total number of patients who had the disease, what proportion or what percentage, if we multiply it by 100, is the number of people who we diagnosed as having the disease? What's this true positive rate? Now, again, I don't remember this by rote. I don't just have this memorized, tucked up somewhere. What I do is I use a little trick to be able to figure out what these mean. So how you can read these is, of the people in the bottom, what is the proportion / percentage where whatever's going on in the top happens? So here, as we read it earlier, of the people who have the disease, what's the percentage that we predict had the disease? And that's the true positive rate, as we're expressing it here. So this is how I follow the interpretations of these concepts when I don't always remember, going back to the equation and putting it back together in this way. Again, of people in the denominator, what's the proportion of whatever's going on in the numerator? So of the people with the disease, what's the proportion that we actually predict had the disease? That is our true positive sensitivity recall hit rate. So we can do this for some of the others. True negative rate, of the people who didn't have the disease, how many people did we accurately predict didn't have the disease? Sometimes this is called specificity, excuse me. The positive predicted value. This one's kind of interesting. The true positive rate divided by the total number of people we predicted to be positive. So if I said that the test was positive, what's the probability that you actually have the disease? I diagnosed you with the disease. What's the probability you actually have the disease? And if we were perfect at diagnosis, at diagnostics, that would be one, but it's not. Sometimes we're wrong. Sometimes we say you have the disease and you didn't really. So what this is asking is, of the people who actually have the disease, or excuse me, of the people who are predicted to have the disease, what percent actually do? Pretty useful if I'm a patient. You told me I'm about to die. Well, what's the percent chance that you're actually right about that? Negative predicted value, same thing, but in the negative. You told me I didn't have the disease. What's the probability that that is the correct diagnosis? And again, this is a good quantities to be able to calculate. All of this we can calculate from the confusion matrix. Now, there is a bunch of other things. The cool part about, at least I think the cool part about the way I process this information is you can actually reverse it back. So you can say, well, I want to look at, of the people who don't have the disease, how many were falsely told that they did? That could be a good thing to check out. Now, I don't know the official name of that, but I do know how to make that proportion because of what we talked about earlier. Of the people who don't have the disease, how many were falsely told, FP, false positive, that they did? That would be FP over N, and that would give me that interpretation. So being able to put this information together and to interpret this can be pretty handy. Again, these are things that actually we use fairly often in medicine, and certainly when we're evaluating new diagnostic tools. And there are some people who are far better at remembering the specifics of all of these things than I am. To me, though, I really try to go back to the definition, what these things mean, and then re-put together, okay, yes, this is why that means that. Because I guess maybe that's a better way to say it, is when we talk about sensitivity or specificity, sometimes it can feel like a very academic or detached conversation. But it actually has a very important meaning, and the distinction and technical details are quite important. So being able to come back to the equation and interpret it appropriately can help to make sure that I am making the appropriate interpretation based on that values listing. Now, based on the confusion matrix, we can also calculate things like prevalence. Now, I don't list this here, but recall that prevalence is the total proportion with the disease. This would be P over the SS, over sample size, the total number of people with the disease. Closely related is incidence. Now, we can't calculate incidence here because incidence is the number of people who get the disease in the course of the period of evaluation. So because this data isn't over time, I can't calculate how many people got the disease over the time. We'd need a before and an after or some kind of interval to determine how many got it. But we can calculate prevalence from a confusion matrix. Now, that makes some assumptions regarding where the data were collected from. But in terms of being able to calculate the total number of individuals with the disease divided by the total number sampled to get a proportion, that can help us calculate. That is our prevalence within the sample. So the big point here is that these small tables, these contingency tables, or this confusion matrix, which is this specific type of contingency table we've been talking about, contains lots and lots and lots of information. That's the main point I'm trying to make here. There's a ton of stuff we can pull out. There's a lot more even than we talked about, and a lot of interesting, good stuff that we can pull out and use to evaluate the quality of the information and the meaning of the information. So even these small tables, when we're working with contingency tables, when we're discussing chi-squared analyses, there's a lot of depth you can dive into here. And I'll just go on and tell you ahead of time, unfortunately, in this lecture set, we're not going to have time to dive into a lot of that depth. We'll discuss some of it. We'll discuss a lot of it, but we won't have time to go into all of the details. So this slide is also a bit of an aside, our last one, and won't be the focus of our class. But with this said, it is also a prevalent topic in the field, and you should be aware of it. Not because odds is something that in healthcare administration, we just sit around talking about odds all day, but because in some of the analyses that medical research really likes, they use odds and odds ratios, which we'll discuss in a second. And the interpretation of these are horrific. So I do want to make sure we talk about them because, again, this is a difficult thing. Now, odds are calculated by dividing the probability of an event by the probability of the event not occurring. So the odds of having the disease, so we have the probability of having the disease, that's our prevalence, would be P over SS, that's the probability of having the disease, and the probability of the event not occurring. So the opposite of not having the disease is, or the opposite of having the disease is not having the disease, excuse me. So that would be N over SS. Now you'll note that for practical intents and purposes, the divided by SS divided by the total sample size cancels in the top and bottom. So we're just left with P divided by N, or the number of individuals with the disease divided by the number of individuals without the disease. And that absolutely works. So often that's how we do odds, is how many people have A, how many people don't have A. And that's how we calculate the odds of having A versus not. Now actually, let me pause on this for one more moment because I want to call out, this has a very different meaning than probability. And often if you think of odds, at least, when I thought of odds back before I had to actually teach this junk, when you think of odds are, you kind of use it in the same way as probability, right? Like, what are the odds? Like, it's involved with some level of chance and probability. And don't hear me say that they're completely unrelated, but they are very different than one another. Like, not just in an academic way, but in a very practical way. They are extremely different than one another and need to be interpreted very differently than one another. And I think this is why I don't like odds, is because that statement that they need to be interpreted differently than one another, that is not something that people really think through. And because of that, we actually have lots of really, really drastically sized misinterpretations. So let's talk through this a bit. Probability is between 0 and 1, right? So, probability 0.5, 50%, probability of 0.9, 90%. It's between 0 and 1, 0%, 100%. Odds start at 0, the same as probability, but they have no upper bound. You can have an odds of 0.9, you can have an odds of 1, you can have an odds of 1.1, you can have an odds of 2, you can have an odds of 3, you can have an odds of 10, you can have an odds of 100. And don't hear me say, oh, this is like 10% or 100% or giving 110%. No, these aren't percentages, and that's part of the point here. Odds are a completely different beast. Odds can go up to infinity. They don't stop at 1. And it's all kind of baked into this equation. So consider an equal number of people in both groups. So an equal number having the disease and not having the disease. The probability of having the disease, if there's a 50-50 chance, is 50-50 or 50%, right? There's a 50% chance you have the disease. There's an equal number of people who have the disease and don't. And I think that makes sense to us. Now, if I just report the odds as a number, the odds of having the disease is 1. Yeah, just 1. And if you think about it, let's say we've got 50 people in each group, again, equal probability. E, the total number of people with the disease, 50, divided by N, total number of people, 50. 50 divided by 50 is 1. The odds is 1. The probability is 50-50. And I don't know about y'all, but that's kind of weird to me. And the reason it's weird, to help you out a little bit, is because probability tends to be how we interpret, cognitize, is that a word? How we process chance information in terms of probability of success, probability of failure, but probability or chance. odds are very different. To kind of drive this home, if you confuse these, and a lot of researchers do, this can cause a massive issue. Now, I don't mean a lot of researchers do in that they think odds equals probability. No, on paper, they could do that. What they do is they use an odds and they assign probability interpretation to it. So consider the problem. Just with our last case, I'll do a better one in just a second here, but consider the problem. We had a 50% chance you have the disease. The odds were 1, and if I interpreted the odds as a probability, I would say you have a 100% chance of having the disease. That's way different. That's a big problem. And if I make a policy decision based on that misunderstanding, that's a drastically different policy than I flip a coin to see whether you have the disease or not versus every single person here has the disease. Those are very different policy decisions. So for a little bit of a less extreme example, consider that you have a probability of like 0.35, 35% chance that you have the disease. And you accidentally calculated an odds and interpreted the odds as the probability. Well, the odds would be 0.54, which is a reasonable sounding number as a probability. And misinterpretation would be that 50% of the individuals in the sample have the disease, when actually that number was 35%. And that's a 19 percentage point increase. That's over a 50% larger value from the original one, that 35%. So this can have a big difference. And again, the misinterpretation is the real problem here. So let me, I'll stop talking about this in just one sec. Well, maybe. But let me talk quickly. What does an odds mean? So if it's not the same thing as percentage chance that you have the disease, that's what probability is, and that's 35% odds in our case of 0.54, what does an odds mean? The interpretation of odds in this context is for every person who doesn't have the disease, odds times as many people do. So in this case, our odds is 0.54. For every person who doesn't have the disease, 0.54 times as many do have the disease. And again, that might be an interpretation that is difficult for you to understand. Consider the probability. Probability is 35% of people have disease. Odds is for every person who doesn't have the disease, 0.54 times as many do have the disease. That's a different interpretation. That's a more complex interpretation. And frankly, it's a less intuitive interpretation. And all of this is why I don't like odds. It's used, and it is so often misunderstood in medical research. It's often misunderstood in applied evaluation reports. Whenever you see an odds, it's tough. So actually, one interesting thing is that odds ratios are more prevalent even than odds. Odds ratios are calculated by dividing two odds. So the odds ratio of having a disease with a positive diagnosis versus without a positive diagnosis is true positive divided by false positive over false negative divided by true negative. And if you think I'm going to reduce this equation to help in a very clever way make it make sense, realize odds ratios have all of the interpretational issues and problems as odds and then some. These are not intuitive. What we want to say with odds ratios when we kind of divide two probability related things, we want to say, well, one group is this many times more likely than another group. That there is a value that has that interpretation. It's called a probability ratio, or sometimes called a risk ratio, and it has that interpretation. This is This group has X number times more than X number times more likely to have the disease than not. So that's the risk ratio interpretation. You are 8 times more likely to have the disease with a positive diagnosis than with a negative diagnosis. That's our risk ratio. The odds ratios are not that. Odds ratios are much more confusing and complicated. So what does this actually mean? For every patient diagnosed with the disease who doesn't have it, odds ratio times as many patients diagnosed with the disease will have the disease, then the number of patients diagnosed to not have the disease will have the disease for every patient diagnosed not to have the disease will not have it. Makes sense? This is extraordinarily confusing. Yeah, so this again, odds ratios interpretations are a pain. That's kind of my long story short here. And my big reason for having this slide is to have this warning. We're not going to talk about odds ratios much outside of this slide in this context. Again, the goals. I want to show you the computation. I want to talk about that. I want to discuss the complexity of the interpretation and ultimately, again, to warn you away from them. Odds ratios, the reason they're used so much, it's not just because people like being tricky. They do have some very nice mathematical theoretical properties. And so some people present these within papers. Some people see these presented within academic papers, and so they echo those methods and present them in reports. Some people use these in see this done online in something like logistic regression, and then want to incorporate that in a report. And it sounds good until you realize that I think in a recent review, something like 20 or 30% of published articles in medicine misuse this. They interpret odds ratios as probabilities. And I think that number was once lower, but I think it's become higher with the advent of modern software. This is a problem. This is a serious problem. And so when you see these odds ratios, or odds, I hope that you're careful. Now, I will post on Canvas one of my favorite articles regarding the interpretation of odds ratios, and it's in the context of logistic regression, which is a popular place for these odds ratios to appear because that's where they have some of those nice theoretical properties. And again, logistic regression outside the scope of our class, but this will help with this interpretation if you're interested. I will say one of my favorite lines from this article, and the reason I'm posting this, it's my favorite line in almost any journal article, is after the explanation of the interpretation of the odds ratio within the context of the problem, similar to what I read above. It says, quote, "Confused? You should be. Unless you work with odds and probabilities for a living, you should find relative risk, the probability ratios we talked about, much easier to understand than odds ratios. Odds are not intuitive like probabilities are, and the language needed to technically describe an odds ratio is, as you see, quite convoluted." End quote. So this is something that is very complex. It's difficult to understand. And again, it's a problem mostly because people ignore the details of the distinction. They take the easy explanation because it's not as convoluted and ultimately end up providing information that's not technically correct. And again, what I want you to think of is our earlier example, the 50% odds of 1. And again, consider if I provide information that's not technically correct, that can change my interpretation from 50% of people have this to 100% of people have this erroneously. And again, it's because the odds of 1 isn't a percentage. It's that weird explanation of the number of people who have this for every person who does not have this. And that's not not intuitive. So I'll close this. My hope is that if you ever see an odds or odds ratio in the future, you have a little orange flag in the back of your head that pops up and says, be careful, be very, very careful. These aren't immoral. They're nothing like that. It's not evil to use them, but they are often misunderstood and misinterpreted. It is, in my experience, in academic literature, it's about a 50-50, but these are people who train to do this. In evaluation reports, virtually nobody interprets these correctly, in my experience, unless they have had professional training in statistics. So hopefully this serves to give you that warning and that heads up to approach these carefully. Again, they're often misunderstood. They're often misinterpreted. So if you see them and you have to use them, do so very carefully. And my strategy is to turn them into those probability ratios. Again, those are called risk ratios formally, because those have a lot easier interpretations. But this isn't always possible. So if you're forced to use these, just have that flag that says, be careful. Remember, this has a complex interpretation. Remember, if you start talking about the probability of or the likelihood of, that is unrelated to an odds or an odds ratio. And remember, we've discussed this in class. Something else we've discussed in class that's also related here is that misunderstanding statistics can be just as harmful as collecting bad data, as running the wrong model, as having an error in the calculation. Misinterpreting it can be just as bad as all those things. So it's very important to be careful. All right, I'm getting off my high horse about this. We can move on. But I think this ends our portion for this lecture video. In the next lecture in this lecture set, we're going to actually start talking about the chi-squared analyses. We've kind of gone through the background information on the contingency tables and the confusion matrix with a couple of side items on some of the calculations we can do from the confusion matrix, as well as a discussion of odds. So in the next video, we're actually going to get into the meat of the analyses in this chapter.